So essentially what I'm going to do in this process is the following. Integral over omega wi comma j sigma ij dv equals integral over omega wi fi dv plus integral over the entire volume, right? Wi sigma ij nj ds. All right. Now, here comes a step that is a little different from what we've done in our previous application to a three-dimensional problem. Okay? What we are going to use is this special decomposition of omega into subsets partial omega ui, which is the Dirichlet boundary, and Neumann boundary. Okay, this holds for I equals 1, 2, 3. Okay, so what this says is that the way we're going to apply this is by regarding this product as a vector with free index I, and then observing that we essentially have in that integrand a dot product of w with that vector sigma n. Okay, so the way I'm going to write that is the following. I'm going to write that as integral over omega. Okay, so let me write everything here. Integral over omega on the left hand side, wi comma j sigma ij dv equals integral over omega wi fi dv plus. Now, because that integrand, when viewed as a final dot product of w with the vector sigma n, right? Because that integrand has 3 terms in it, right? For I equal to 1, 2, 3, we are going to write each one of those contributions to the dot product, right, separately, right? So I'm going to write that as each of these decompositions of the boundary, right, are going to be used to give us the domain of integration for each integrand. Sorry, for each contribution to this integrand, right? Okay. All right, so the idea is you fix I, maybe I equals 1, right? So you do the integral by viewing our boundary as a union of these 2 subsets, boundary subsets, right? But in computing that integrand, you compute only for a fixed I. Okay, so you fix these guys, right? These are fixed. Okay, fix everything, right? So fix all those i's. Now that gives you the integral with just one of those components. You need to have all the components and you do the sum. Right? So far we've just written that integrand differently. Okay? That's all we've done. Sorry, all we've done is write that integral differently. Okay, but now we can do something nice, right? And what is that? We invoke our boundary conditions, right? Now we invoke boundary conditions on wi and sigma ij and j. Okay? Right? And remember the way we wrote those boundary conditions. Okay? essentially the way we wrote those boundary conditions say that now that we're integrating over each special decomposition of the boundary, what we can do is this, right? So let me actually go to the next slide. So what we can say here is the following, right? So we have integral over omega wi comma j sigma ij dv equals integral over omega wi fi dv. That term's got to be the most tame term we've ever encountered, right? The forcing function pretty much does nothing. Okay, plus sum I equals 1 to number of spatial dimensions. Integral. Now, I'm going to break up that integral, right? Because we've written it on the previous slide as an integral over the union of Dirichlet and Neumann boundary subsets, right? So I'm going to write it as integral over partial of omega ui of wi sigma ij nj ds plus integral over partial of omega t bar I wi sigma ij nj ds, and I close my parentheses here. Okay, and actually looking at what I've saved here for my previous slide, I'm going to go back for just a second because I realized that I did not put my elemental area on that integral. Okay, but you may have got it. All right, here we are. All right, now is when we invoke the boundary conditions on wi. And what is our boundary condition on wi over the corresponding Dirichlet boundary? It is that it vanishes, right? And what is our boundary condition on sigma ij nj over that part of the Neumann boundary? It is that sigma ij nj equals the t bar I component. Okay, and so we have it. We have integral over omega wi comma j sigma ij dv equals integral over omega wi fi dv plus sum I going from 1 to number of spatial dimensions, integral over the corresponding Neumann boundary only, wi t bar I ds. Okay, this is our weak form, right, which we've derived from the strong form. Like I said, we can go back the other way. It's not something we'll get into here. I will make one remark though, which is that just as we did in our little treatment of variational methods in the context of the linearized elasticity problem in 1D, right? We demonstrated there that the weak form could be obtained through these variational arguments of extremization of a free energy functional in 1D. Exactly the same thing holds in 3 dimensions as well. Okay, so the weak form can be obtained as the so-called Euler-Lagrange conditions the Euler-Lagrange conditions of a variational principle right? And what is the variational principle? Well, it's not minimization necessarily, but it's extremization on extremization of a free energy functional in 3 dimensions. The problem we treated a few segments back, quite a few segments back, quite a few units back, was in 1D, but essentially all those arguments hold in 3 dimensions. And actually this is a very powerful approach. While in the case of the simplest formulation of linearized elasticity, it doesn't give us anything that we can't get through other methods. Something you may be aware of is that there are so-called constraint problems, right? And a common constraint on linearized elasticity is incompressibility. So if you're dealing with a linear elastic material that's also incompressible, it emerges that the methods we work with, the standard finite element methods we work with and that we will be developing now, do not work well. Okay, and there are fundamental pathologies which arise. These are very well understood, and methods to circumvent that difficulty, right, are based upon defining more generalized versions of these free energy functionals, introducing more fields and working with them. It's the domain of what are called mixed methods. Okay, and it's a very powerful approach in which arises from the variational basis of the method. Okay, but we won't be getting into that in this entry-level series of lectures. Okay, the very last thing I want to do is just go from there to putting down the finite dimensional weak form. Okay, so what we have here, what we've just derived, is the infinite dimensional weak form. Okay, the finite dimensional weak form follows, right? And now, of course, we're quite expert at doing this, and you know exactly what's going to happen. It's going to look no different except for the specification of spaces, right? But let's just put it down so that we will be able to move on with the formulation. Okay, the finite dimensional weak form. As before, given UGI T bar I Fi, the constitutive relation sigma ij equals C ij KL epsilon KL, right? That's the form of the constitutive relation. Let me state it. That's a constitutive relation, and the kinematic relation epsilon KL equals the usual stuff. right? Given all this, find. Now here's where things become different, right? So actually let me put it on the next line so that we can give it its due attention. Find UH sub I, right? And as always, that superscript H reminds us that we are talking of approximations, and H is going to be related to the element size. Okay, that's all it denotes. Okay, find UH of I belonging to SH, which is a subset of S. Okay, and what do we mean by SH here? SH consists of all functions. Now we further require, as we've done before, that we are interested in functions that are H1 over the domain. Okay, and of course they must satisfy in this class of finite element methods that we're working with throughout the series of lectures. We do require that they satisfy the Dirichlet boundary condition on the relevant subset of the boundary. Okay, so find UH of this type such that for all WH sub I belonging to VH subset of V. Okay, and what is VH? VH consists of all weighting functions, also H1, such that WH of I equals 0 on the corresponding Dirichlet boundary. Okay, so find UH belonging to SH such that for WH belonging to VH, what holds? Well, the weak form that we wrote before, except with all the relevant fields replaced with their finite dimensional versions. WHI comma j, sigma HIJ dV, right? And we recall here that sigma Hij is simply computed by as C I J K L epsilon H K L. Okay, and what is epsilon H K L? Well, it is just obtained from this relation with UH. Okay, all right, this is equal to integral over omega, sorry, this is over omega 2, WHI Fi dV. Okay, remember that as before, we do not consider finite dimensional versions of f, right? The f is part of the data and we take it as given. Plus sum over the spatial dimensions of the integral over the Neumann boundary of WHI T bar I ds. Again, because T bar is part of the data, we don't try finite dimensional representations of it. Okay, this is it. Just for completeness, let me squeeze in here that epsilon H K L equals that. This parenthesis closes that one, and this closes that entire note. Okay, all right, we are done with this segment. When we come back, we will just work with this to develop our finite element formulation.